Today's video will focus on determining how a derivative can tell us something about the original function f. In other words, how derivatives affect the shape of the original graph. First, let's look at a graph of a derivative. Now keep in mind this is f prime, not f. From negative infinity to negative 2, the derivative is a negative y value. And then from negative 2 to 7, the derivative is a positive y value. Then from 7 to 12, it stays a positive y value. And then from 12 to positive infinity, it becomes a negative y value. Keep in mind your derivative values are the slope of your tangent lines. So what this is saying is in this first section of graph, we must have negative slopes of our tangent line. Then at 2, we must have a horizontal slope of our tangent line. And then once we have positive values, it means we must have a positive slope of our tangent line. And that will continue all the way till 7. Notice, though, it has a horizontal tangent line for a second and then stays positive. So we'll have more positive slopes. And then when we get to 12, it becomes negative slopes again. So let's go through this again. Over on the left, up until negative 2, our original graph should have negative slopes. At negative 2, it should have a horizontal slope. From 2 to 7, we should have positive slopes. The slope should be more positive for a bit and then become less positive. So that means it should get a little steeper and then become less steep. At 7, it's a horizontal tangent for a second and then stays with a positive slope. So that's kind of like what happens at x cubed is going on at the 7. So we stay a positive slope until we get to 12, where there's another horizontal tangent line. And then we have negative y values for our derivative, meaning there should be negative slopes of our tangent line, causing it to go back down. So what this really tells us is in this section, our original graph was decreasing. In this section, our graph was increasing, and then all the way to 12, it was increasing. At 7, because there's a horizontal tangent line, it is neither increasing nor decreasing. And then from 12 on, it's back to decreasing. So the sign of the derivative, whether it's positive or negative, can tell you whether it's increasing or decreasing. Now, at negative 2, we went from decreasing to then increasing. Well, if you switch from decreasing to increasing, that causes a minimum to occur. So at negative 2, we're going to say that we went decrease to increase, so we had a minimum. At x equals 7, we went from increase to increase. So all that tells us is we have a horizontal tangent. Because it did not switch from increase to decrease or decrease to increase, it doesn't give us that minimum or maximum. And lastly, at 12, we went from increase to decrease. So we increased and then decreased. That caused us to have a max. So whenever you're given a graph, whether it be on a test, a quiz, on a homework, it's important to note, are they giving the graph of f or f prime? Because it tells you different things. If you're given a graph of f prime, where the y values are negative, the original graph is decreasing. Where the y values are positive in your f prime graph, your original graph is increasing. And where the y values of your derivative are 0, we should have a horizontal tangent line. And we've been using that fact already for a little while. And here's a look of an original graph f with some slopes drawn in. Notice where the graph is increasing, it's all positive slopes. So they would be positive y values in the derivative. Where it is decreasing, there are tangent lines with negative slopes. So the derivative would have negative y values. And then it goes back to positive slopes once again. So notice where it went from positive slopes to negative slopes, we had a max. So in other words, when your derivative goes from a positive value to a negative value, and when our slopes went from negative to positive, we had a min. So in other words, when your derivative goes from a negative value to a positive value, you'll have a min. So as we saw, f increases when the derivative is positive, f decreases when the derivative is negative. And here we have it written nice as a theorem for you to copy down. If the derivative is greater than 0, so in other words positive, then f is increasing. And the reverse, if it's less than 0, so that means negative, then it is decreasing. So let's see if we can determine where this function is increasing and decreasing. We've seen that the derivative can help us determine that, so let's go ahead and take the derivative. We'll get 12x cubed minus 12x squared minus 24x. Well, what we want to do is we want to see first, where is the derivative 0? That can tell us where the horizontal tangent lines are. So we can pull out a 12x, leaving us with x squared minus x minus 2. Which will factor into x minus 2 and x plus 1. When we set each part equal to 0, we'll get that we'll have horizontal tangent lines at x equals 0, x equals 2, and x equals negative 1. Those are the values where we could possibly change from increasing to decreasing. So we'll put those values on a number line. We'll have negative 1, we'll have 0, and we'll have 2. Now, because we had a polynomial, we didn't have to worry about this, but if you ever have a case where the derivative is not going to exist somewhere, remember that's also a critical number that you would want to put on your number line. Because this is a polynomial function, the derivative exists anywhere, so we didn't need to worry about that in this case. What we will do is we will pick test numbers in each of our gaps to determine the value of the derivative there. We want to know in each section, is the derivative going to be positive or negative? So in this section here, we can pick something like, say, negative 2. Plug it into your factored form. That will be easiest. When you plug in negative 2, you get back a negative, and a negative. Well, a negative times a negative will come back negative. In between negative 1 and 0, we can do like negative 0.5 in this section. Again, test in your factored form. 12 times a negative 0.5 will be a negative. Negative 0.5 minus 2 will be a negative. Negative 0.5 plus 1 will be a positive. Again, we don't care about the actual numbers. We just want to know if it's negative or positive. A negative times a positive will come back positive. Pick something like 1 in the next section. You'll get back a positive, a negative, and a positive, which will come back negative. And maybe pick something like 3 in the last section. You'll get positive, 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 which will end up positive. Now keep in mind, the thing we just had on the previous slide was that if the derivative is negative, that means that the function, the original function, is decreasing. And if the derivative is positive, that means the original function is increasing. So based on this, knowing where the derivative is negative and positive, we can list where it is decreasing and increasing. We are decreasing from negative infinity to negative 1 because it's minus in that section. Now notice we have rounded brackets because we're not including that negative 1 because at negative 1 it is neither positive nor negative. And then we're negative again from 0 to 2. So those are the intervals where we are decreasing. Your increase intervals are where it's positive. So we are increasing from negative 1 to 0, and then again from 2 to infinity. Now the little u just means the union, saying it's both of those parts where it's increasing or decreasing. Now, keep in mind that just because it has a local max or min at a point, or keep in mind that our critical numbers can tell us where the maxes and mins might be, but every critical number is not a max or a min. So we must have some type of test that will tell us this. So you can see, looking at this original graph of an f, okay, an original function, our minimum occurs when we go from decreasing to increasing. And our maximum occurs when we go from increasing to decreasing. So a minus to a plus will cause a min, and a plus going to a minus will cause a max. And this is what will tell us where we will have maxes and or mins. So here's an example. We're changing from a positive slope to a negative slope. So it's going from increasing to decreasing, so we have a local max. Here we change from decrease to increase, so we have a local min. And here we change from increase to increase or decrease to decrease. So notice when we don't change from one to the other, we do not end up getting a local maximum or minimum. This would create the case where it's just a horizontal tangent line. An x cubed or a negative x cubed function is a good example of one of these. So to put it all together, this is our first derivative test. If the derivative goes from positive to negative, we know then we have a local max. If it goes from negative to positive, we have a local min. If it goes from positive to positive or negative to negative, we don't have anything. We just have a horizontal tangent line there. So let's go back to the example that we did. This is what we had on the previous slide. We had that this section was a negative, this was a positive, this was a negative, this was a positive. Well, when you go from a negative to a positive, it creates a minimum. So we're going to have a minimum. And keep in mind, we only know that they're locals. We aren't guaranteed that they're absolute. So local min at x equals negative 1. When we go positive to negative slope in our original, it'll create a max. So we'll have a local max at x equals 0. And then we've got another local min at x equals 2. Now, depending on what the question asks, that might be all you need to find. It might say determine where the maxes and mins occur. Our particular question tells us to find the local maxes and mins. So for our mins, we've got to actually see what is f of -1 and f of 2. And for our max, we've got to actually see what is f of 0. Now, your maximum and minimum are y values in the original function. Because they're y values in the original function, we need to plug back into the function f. When we plug -1 in, we'll just get back 0. When we plug 2 in, we'll get back -27. And when we plug 0 in, we'll get back 5. So we could say that we have a local min of 0 occurring at -1, and we have a local min of -27 that's occurring at 2. We have a local max of 5 occurring at 0. So the max and min values are the y's. Where they are occurring, those are the x's. We'll look at one last example. We'll see if we can find the local maxes and mins using our first derivative test for this function. We have worked with this function before when looking at absolute maxes and mins. We'll go ahead and take the derivative, which will give us 1 plus 2 cos x. We'll set that derivative equal to 0 to find the critical values. There are no values where this function will not exist because cos x is defined everywhere. We'll subtract the 1 over and divide by 2 to get that cos x is equal to -1/2. Using your ASTC, that means we're working in the second and third quadrants. A 1 and 2 comes from a 30, 60, 90 triangle, with the 1 being across from the 30, the 2 across from the 90, and the square root of 3 across from the 60. We want a cos of 1/2, so that means we must be working with 60. So we're working with a 60-degree reference angle in each of these quadrants. Well, 60-degree reference angle means we're doing 180 minus 60 to give us 120, and 180 plus 60 to give us 240. Keep in mind we need to work with radians, though. So we need to multiply these each by pi over 180. Again, you always just multiply in the numerator by the way that you're going. We're trying to go 2 radians, so the radian is in the numerator. And this will give us 2 pi over 3, and this will give us 4 pi over 3. And what those are is the values for our number line. Now, because the question said from 0 to 2 pi, we'll also stick the 0 and 2 pi on our number so that when we pick test numbers, we don't pick it outside of that span. So we'll be plugging this into our derivative, which is right here. A nice value to test in here would maybe be something like pi over 2, which is like saying 90. Cos of 90 is 0, so that wipes out the 2 cos x, and you just get back 1. 1 is a positive number. Something nice in the middle here would be pi. Cos of pi is -1, so you'll get 1 plus 2 times -1, giving us a negative. And something out here is 3 pi over 2. We're again back to 0 for cosine of 3 pi over 2. And where these are each coming from, these values, is just from our cosine curve. So because 3 pi over 2 gives you 0 for cos, we'll just end up getting 1 back again, which is a positive. We are going increasing to decreasing at 2 pi over 3, which should give us a max, decreasing to increasing at 4 pi over 3, which should give us a min. So we know we're going to have a local max when we plug in 2 pi over 3, and we'll get a local min when we plug in 4 pi over 3. Now keep in mind we have to plug these into our original. So we're doing x plus 2 sine x. When we plug 2 pi over 3 in, 2 pi over 3 will go in for x. And we'll do 2 times sine of 2 pi over 3. Remember, 2 pi over 3 is 120. 120 is in the second quadrant where sine is positive. And there's a 60-degree reference angle. So a 60-degree reference angle for sine would be square root of 3 over 2. So we'll really just have 2 pi over 3 plus 2 times the positive square root of 3 over 2. Again, because sine is positive in the second quadrant. So that'll give us in the end 2 pi over 3 plus square root of 3. For the other one, it will be similar. We'll have 4 pi over 3 plus 2 times. It'll be the same reference angle, but now in the third quadrant, sine is negative, so it'll be a negative square root of 3 over 2 that we're multiplying by. So in the end, this will give us 4 pi over 3 minus square root of 3 for our minimum. So remember, the y values are your max and your min. The x values are where those maxes and mins are occurring. That's all for today's video. We'll see you next class period.